synthesize all the devices, and you don't use all this capability. Waste of energy, because when you start a device or gateway, there is a minimum energy you use, and after if you put some processing, you don't consume too much energy. So you can use also this processing capability at the level of the devices. So in 2012, the fog computing models have been introduced. The Open Fog Consortium proposed a definition. So it's a system-level horizontal architecture that distributes resources and service anywhere around the continuum from cloud to SIG. In 2017, NIST also proposed a definition on the description like this. We see a different concept for computing, edge also. So it's aware of the model of for computing. What is difficult? You have different kind of equipment, cloud, fog, devices. There are different capability in terms of energy, processing, communication, memory, and storage. And you should manage this when you deploy all the services to get a good one at the good level of decision on the capabilities. So the goal is how to use this architecture when you want to deploy complex services and offer these services to application. So we have a user, we have an application. This application needs several kinds of services to be developed. And we have also an infrastructure with a platform with several services. On the same services, for example, can be at a different part of the architecture. And we should select the good one and make a composition of these services between with the other services. So the goal is to manage this IoT system, to take care of dynamic and to make an on-fly composition. Also to be able to combine heterogeneous services, that means software, also services in terms of sensors, value, devices, middleware systems. We want to discover services at the fly, and also take care of QoS, quality of services, and some constraint on specific system. So service composition is not a new domain. It exists for several years in the web service, for example. But in the existing approaches, most of the time, you know exactly the set of services that you can use. It's not the same things in IoT. You also, most of the time, have a workflow predefined. So you know you need to have this kind of service after this one, and you just select at the good time the good services and make this exactly this kind of service. And in fact, most of the time you do some selection, choose the good one, and make the connection between services. With IoT, the problem is the services can arrive, be curated, input, output of the services can be different. And you need also to choose these different services in terms of input, output, on its move and change your workflow. So you need also to build the workflow at the dynamic time. So what we want to take care is about mobility, dynamicity, involvement of the system, and to make an automatic decision on connection between the different services. One of our use cases is S2C2. It's a national program on collective vehicles, this company. So we develop an ecosystem inside the city. We have some different middleware, different platforms that communicate each other, that can give you information about the city, about the weather, all you have in the city. You have also some different kind of car. You have some collective vehicles, but also bus, bicycle, and want to produce new services for all these kind of vehicles. So this is the platform we use to show how we can manage IoT system and dynamic services. So the first system and principle that we want to use It's autonomic computing loop. It's based on a concept developed by IBM in 2003. And it's a way of managing a system and act on the system. So you observe a system, you get some information, some event. You do that, you connect this event to a block called monitor. The monitor is able to make some reasoning about the event. So for example, if you have several times the same event, you can say, well, this is the same one, I keep only one. You can make also correlation between different kind of events. And with those events, he will create a symptom, say, well, there is a problem to solve. And he gives this information to a block called analyzer. This analyzer will also use a knowledge base to see what we can do to resolve this problem. When he has the answer, he makes a request for change to say, well, we need to modify this kind of thing inside the system. This request for change is sent to a planner, and the planner will take a decision, what I can do with the real system to change this and make an action on the real system. So you create a plan, and this plan is sent to an executor, and the executor will translate all this simple action in terms of request on the IoT system. So it's a way to modelize an action system based on a knowledge base. This is the core of the system. And in this knowledge base, you can do some reasoning, you can use some specific model as a Qt system, what you want inside. For this work, we work on ontology, on the graph grammar, to modify the ontology. Second concept, ontology. So you have some data that are collected from a system. We have also an ontology that describes with the vocabulary the concept and the relation between all the concepts. And the goal is to make reasoning using rules to create a new knowledge. This is basic concept inside the ontology. So we use this to collect information from the IoT system. We have defined all the relation on what we can understand about the system, and we create a new relation inside the system. So we propose an ontology. This ontology is based on a previous ontology that we produced called IoTO, public ontology, to represent the IoT system. And on this ontology, we had some new concepts. So one, you have an entity inside the system. You are a consumer of services. You can express some interest. I'm interested for example, I'm interested about museum inside the city. And this topic will be translated in terms of content. Who can produce a content of information about museum? And depending of location, for example, inside the bus, I will get information about this museum, and I produce this information and put this information on a display. So we have some user, express content, we have some service and devices that are able to propose this content on a specific display. So, an example, we have a person who express an interest. This interest is produced by this content, and we can use these services to get the content. We have also this person one that is inside the bus, and this bus also is able to produce some content, and is also connected with different devices. So we have a representation of the system. This is what we can collect from the real system, for example, using OM2M, where we have a description of all this information, all of this information. Then we produce some rules to infer new knowledge. So, for example, the consumer is interested in this topic. This topic is able to be produced for collective people. This topic is related with this content, and also from now, we are located in this place. We are near the museum, for example. Because the consumer is inside also the bus, and the bus is in this location, we should send this content to the user. So this is a way of reasoning on the ontology and to produce this kind of things. We have the first diagram to expose interest on the relation between devices and entity, and then making reasoning can show that because this person is on the bus is able to produce this kind of content, we can make a relation between both entities. So this is the first level of reasoning. We need to know all the connection between each entity inside the system, each services, and infer knowledge about this. Then we need to manage this entity, so to make a request for change, to make the connection between the different services, to propose the contents to the user. So we use services, also material in terms of devices, gateway, and display of things. We use also some specific operation, like a merge. If a content is interesting for several people, we will merge this information to put on the same display if all the user can see the display. So also, it's a bit different with composition of services, classical composition of services, the capability to merge different entities that are interested in the same content, in the same services, in fact. So we only run one time the services and share with all the entities. And the goal is to produce an executable graph where we can make some real action on the real world. To do that, we use graph grammar rewriting rules. So in this methodology, we have some rules that describe an evolution of the graph. So we change in the graph this kind of pattern, and we replace with another pattern. So like this, we change the graph and make a simplification inside the graph. We also have some rules where we can say if we have this condition, we don't apply the rules. It's not applicable. So with many rules, we can manage the graph and create, after the ontology graph that we can extract, we make some transformation, and so that, in fact, this both content will be merged on the same devices because users are in the same bus and so the same display. And we can optimize like this the use of the services. Just ontology, we simplify, and after we make a proposition of plan using graph grammar. So we do that in the monitoring. Depending of where we are in the MAPA loop, we use the different models to find the execution, and then we send some request, REST request to OM2M to display and do the things inside the bus. We make a first prototype, so a mock-up. So we have different location. So it's to modelize bus planning inside the town. We also have some different kind of interest in terms of weather, air quality, and also some information about some activities inside the city. In the bus, we build some display also, and we manage also some cars to detect that people are inside the bus or outside the bus. And we make different kind of experiments. I just show this one. So we select a different number of contents. So it's a way to have a different size of ontology and knowledge inside the ontology. We also use different number of passengers. So if we think about a bus, take no more than 60 people inside the bus. 100 contents different that can be interesting for user. And we try to see how long does it take to make the reasoning and the connection between the different services. So at the maximum, when we have 60 people inside the bus and 100 different contents to manage, it takes less than a few seconds to do that. This is important in terms of ontology, because it takes a lot of processing. And when you have a very big system in terms of information, it can take more than an hour to get the information. So using fog computing, we can make this decision at a local place inside the bus and have a quick response to manage this. If we go at the cloud level, we can't get this because there is too much information inside the management of the system. So this is a proof of concept in terms of management of services. So really to do that, we need to have fog architecture to manage scalability. We have started to work to develop more generic and more complex reasoning during my stay at UV, Nicolas. So we try to write a new publication on this to manage different kinds of devices and systems. I also another PhD work on the concept of avatar. The goal is to have a virtual abstraction of a physical object, and the avatar is able to make some reasoning using, for example, semantic, and also is able to connect to other avatars in the system. So we work on this also on a connected vehicle, a company called Continental, to develop a new capability inside the vehicles. So the goal in this avatar is to have the autonomic loop and to make some reasoning, but also to have ability to connect and to exchange with the other avatar to make common decision when it's necessary to do that. We also work on the integration of QoS metrics and also the distribution of knowledge over a fog. So this is also a PhD that's finished now. And the PhD student said he will defend his PhD in November. So the goal is when we collect all this information, when we want to do some reasoning, we don't need to do the reasoning at all time at the same level. So depend of information, depend of capability of the devices, we need to change where we will do the reasoning. So the goal is to distribute information, but also the rules on reasoning, and to migrate all over the fog, depending on the specific condition at one time. And we prove that we can do that on the manager. We also work on simulation on fog architecture. To do that, we use the iFogSim. It's an extension of CloudSim on a work on the past with the University of Melbourne on CloudSim, the cloud team. So now we try to modelize our system using iFogSim to see and explore time prediction of time response and also energy consumption inside the fog. We have also some work just started on cooperation with another lab of using natural language to have interaction with people. So how we can manage in an IoT system. We want to have some autonomous decision, but also we have a human, and we need sometimes to have an interaction of human. And we try to use also ontology and natural language exchange with the IoT system. We have also for demonstration about this. And finally, we also want to work on interaction on robot and also to manage autonomously the service. So we have done the first work on this. Just show you. So we have a building called a Dream. It's a smart building with many sensors inside. And also we have some experimental place where we can manage robots and the system.
You are in the last Dream building, a smart and connected building. I am here to show you how I can use the connected objects that are present in this flat. Here is the most recent information I have about the Dream building. The outside temperature is 16 degrees Celsius. Our
robots make some exchange with the building
production is
general information.
5,343 watts. The building's power consumption is 20,299 watts. The temperature inside is 25 degrees Celsius. Now I am going to explore the bedroom. I have seen the red sensors. I have seen the smart wall plug.
Now you discover all the IoT system inside the building. To do that, in fact, you have some look on tags. With this tag, you know how to connect to these devices.
I have finished exploring the bedroom. Shutter presence sensor, 0 kilograms. That was the ambient plant 1.
Switch light.
That was the fan. Find the object, red sensor. It is cold.
Now it's an interaction with human. Okay. You need to find devices inside the building. Also, we have people who work on false detection.
Warning, John fell in the bedroom. I am calling for help.
The robots have his own representation of the world inside the flat, where is the human, where is all the devices. So this is the first step. And now we want to make this dynamically. We want to make some reasoning to know how to interact and have some complex scenario with the robots. That's it. So now Fabian will show you how we can use OM2M. It's a framework to connect devices of different kinds.
Thank you, Thierry Monteil. So, hello everyone. My name is Fabian Ho. I'm a student in 4th years in engineering school at INSA in France. The name of my project is OM2M Architecture for Smart Bridging. And my supervisor is Senior Professor Thierry Monteil, Senior Professor Pascal Perez, Dr. Nicolas Vestabel, and Dr. Joan Barthélémy. So, today, in this building, we have several protocols of communication, like LoRa, Sigfox network, or Bluetooth network, Wi-Fi network. And for example, for LoRa network, we have a lot of data. We have 25 sensors in building, and we can have more than 2 billion data by day in the database. So, but on the middleware. We have a middleware by a protocol of communication. For each protocol, we have their own middleware. And like this, it is our context. Now, I will give you one question. If it is a use case, so we have one network LoRa, one their own gateway and their own middleware, and their own server. So I want to add another protocol, how I make it. So I need to implement a new middleware for a new protocol, which is how I make it with kind of middleware. Now, another use case, I have two protocols and two middleware. And I want, for example, take a data for application 1, API 1. I want to take some data on LoRa and put this information on the network of Bluetooth, for example, to open a line. So how I make it? I need another application interface to make this communication between them. So it is a problematic. It is problematic. So my solution is to use a OM2M standard. So I use OM2M Eclipse. It is an open source platform for M2M interoperability, and based on the OM2M standard, one M2M standard. He follows the RESTful approach, so all is in HTTP. And he's very interesting because it is a middleware which can put on the top of system or on the top on application, like the gateway of network of Bluetooth. And another entering point it can be extended via plugin, like a plugin for communicate middleware with a LoRa network, this middleware with a ZigBee network, for example. So it's very interesting. So now I will explain you how I make it In one-to-one architecture, we have virtual visualization. So, for example, we have one application of smart meter. We have his middle node on the top. He contains different applications. For now, we have one application, smart meter. Inside, we have different containers. We have one container is descriptor. It's like to have a metadata, and one container for data. And inside data, we have a container stand. We have a notifier of data or data is string. So I manage my implemented to have this kind of choice. I implemented with didn't want a data duplication. I want to limit it to the HTTP request, and I want one vision with architecture by bridging and then grow. So I will show you how I make it. How is it? So we have one-to-one service. I'm logging. So we have a faster smart campus. So it is a infrastructure of smart. Inside, normally we have a lot of bridging. So access of imaging 6. Inside we have ICP. ICP it's access control protocol. Inside we have those who have access on this data. Description of all the sensor inside the bridging. So the display, so what is it? Unity of envelope is metadata. And then we have, this is one application I explained you just after, is to have a median of the data of the building and each room. So in each room, all the room, we have different applications. So it is the data flora. So a description of ID. So all the room have a sensor, this ID sensor, and we have a data of the room. So all the data have some label like movement, pressure, size, temperature, voltage, and I can choose the latest data of the older data. If I take the latest data, I can have the different attributes of temperature and his value. So it's like this. So it's like this. So now I will explain you some application you can do in this architecture. This is one use case. You have in the room different data, like temperature, humidity, voltage, movement, so we have some people inside or not. In the building, have a lot of room. And I want to recover just all the temperature in each room. How I make it? So I use the label on the one-to-one. So like, for example, I want to recover latest data with a label like sensor temperature or sensor voltage. And my application, I take one treatment, it's to take the median of the data, to have a median of data of the building. And after I post on the tree resource. It's like this. So on my tree resource, I can show, so I come back, I can show my median. So I take my rest, and we have around 20.8 degrees in this building, humidity of building, pressure or voltage of each sensor. And so this is one application you can make. Another thing, oh yeah, sorry. And how I put my application, I put my application on my architecture in the infrastructure node. It's my access point where so I ask, I want to take my all the data with a label sensor temperature, and it responds me, and I post again on the tree resource. Then another use case. So in the room have different protocols of communication and a lot of data, a lot of room in each region, and I want to make a simple application and a complex application, but do it easily. How I make it? I have one solution is to use a node RED. So I want to show you how I make it a simple application and complex application with another. My first example is to take the temperature of room 23 and send the email. This application, just I put again on the EN the server. So on my notebook. So it is Node-RED. It is the application we use with Flow. So here's the time slide. I put on or off. I choose my room. In my room, I say where is it? My tree on my resource tree in my one-term architecture, and my log if I can access or not. After I take in where application, it is what is the container I want. I want to take a lattice or always. I take a name. It is an extractor to take just a value I wanted, so it is the GPath. So like this, I can put, and I know in the room 103A, so it is 20 degrees and more. So I can show two, so it is one graph, you can show a sample. So you can have with Node-RED a sample dashboard or like this. For example, I can send the email with Node-RED, like the temperature. I take one switch, it's because I say if my temperature is behind that 25 degrees, I want to have one, send me one message. So I send, for example, Pascal Perez. I say on the switch, I choose, so behind here, so 25. I say that like this. And I deploy. When I deploy, I send a message. So the message is sending. Just come back to the data tab. And normally, Pascal Perez we have the mail of his temperature of his room. So you can make a complex application with like a dashboard. So it is like here we have some information of system, different bridging, information of bridging, different information of building, sorry, and different information of room, like temperature, as I say, as I'll show you after. It is the actuator, so I want to open the light. And we have another application is subscription. So with Node-RED and one-to-Web, you can say notification. So if I subscribe of this container, when the container is changed, he can notify in the HTTP server. So on my dashboard, so it's like this. So we have the system here. You can choose a event. You can choose what is it, the smart messages, send an email. You can choose the bridging you have, so G6, so information of bridging 6, and the graph coming, so it's here, so it has 20 degrees in this building. You select your room, for example, room 103, have temperature and humidity, SSE, like this. So you can make a complex dashboard with a sample software. So my question with one-to-one. It is very interesting because he is very extensive via plugin to speak a different protocol. Each plugin can make a specific functionality like remotely installation, status, stop, update without working the robots. He used also the RESTful API to make authentication, discovery, access rights, different group. And the important point is interoperability of the data. We can have a different data. My realization on this internship, I make an implementation of one-term architecture on this building. We can have a data collection on the web-to-web and a visualization with the dashboard, so with the sensor deployed on this building. For a future perspective, you can make implemented on the different smart campus, implemented one-term standard in the different smart campus to exchange the data, to know what is the difference between this campus and our campus, and how we can manage. And so I'm finished, and I want to say thank you for your attention. I want to say thank you of Thierry Monteil, Dr. Nicolas Verstevel, Joan Barthélemy, and Pascal Perez to let me my internship in Australia, and thank you for you too.
I can confirm I received the email.
Thanks, you too. Questions? Is the code available anywhere? The code?
The code?
Yeah.
Of
What you've done?
so it's the code of Web2N. It is simple to install. It is just a software. So on your building or smart campus, you just start with the middle node and another place with your infrastructure node, and he remotely directly on the three resources. And just after, you have some API to put your container inside your resource tree.
Cool.
And you can manage how you want. So a container can have a container, and container have a container instance. How you want.
The protocol is open source. The implementation of the protocol is open source, and even the plugins libraries are open source.
Yeah.
Cool.
Terry. I'm working on a project to try and get like a model to simulate catchment processes, and one of the products that we want to get from that model, which gets input from a whole bunch of catchment-wide sensors. One of the products we want to get from it is a flash flood warning system, which gets around problems to do with warning fatigue in short response time catchments, which means if we wait for the gauge data to tell us we're having a flood, and then we push that warning to people, it's too late for them to evacuate. We put them on the road instead of their house. So we're thinking of combining a predictive system, which is much less reliable. It uses radar rainfall to tell us we have conditions developing that could result in a flood, and then push that as a warning to users. And then maybe give the users the option to connect themselves to like a pre-configured set of sensors in their catchment, so that they can then get the real-time data, but they're primed. So in real terms, they get maybe 2 hours warning that a storm front is approaching that could develop into a flood. But 90% of those warnings, they're not going to need to action. But we want to avoid teaching people to ignore the warnings by giving them a quick and easy way to connect to the actual real-time data, so that if the shit's really hitting the fan, they get a more strong response that says, this time the warning was real and you need to act. But it needs to be processed information. There's two ways to process it. Either we educate the people very strongly beforehand, so they can look at their phone and say, okay, I know where these gauges above me, I know where these water level gauges and where these pluviometers, rain gauges in the catchment above me are, and I've educated myself so that I know what that depth of rainfall means in terms of flood levels at my property and how long I have until that happens. It's very difficult for us to educate a lot of people that way. It's also going to be very difficult for us to, even a very fast hydrodynamic model, it's going to be very difficult for it to run on demand. So when a user says, oh, I have got sensor activity in the catchment above me, now I'm asking the system to process this information for me and give me a location-specific information about how long I have until what depth of flooding has occurred. What you were showing us earlier with the fog computing about the different people on a bus, how two users who have something in common, whether it's the content of their query or their geographical location, their queries can be put together and compounded to produce a single response. Is that the sort of thing that we could use if we had two people who live near each other in the same catchment? They're both getting messages to say that you have a risk of flooding. They both make a similar query that says, okay, well, tell me if it gets more serious, but give me more accurate information. How feasible is it that we could have a cloud system that would collect everybody's, run the model once, and then distribute location-specific information, even though people may be in different places?
I will understand the question. It's more perhaps on what we want to work with Nicolas in terms of context, to define, in fact, a context where we can put location, we can put what we want to share with each other, what are the context environment but around us, and to say, well, if we have the same context, we can share information, we can share deduction. So we put this inside the context notion to make the connection between every entities that need to interact each other. Starting work, in this work, just work on location. Say, well, we know you are in the bus, for example, because you have your card and you tap on, and we know you are in this bus. We know the bus because there is a GPS and inside the bus. So it's quite easy to make the reasoning on these kind of things. I think for you it's more complex because you have several.
No, if we use the bus analogy, say there's 6 people on the bus. They're all going to 6 different locations. There's a car accident and the bus is slowed down. There's a model that predicts how late the bus is going to be. Everybody on the bus says, how late am I going to be, but their destinations are different. That would be analogous. So run the model of how delayed the bus is going to be once, but each user gets a different result from that model because their objective is different.
So ID is a good use case of how you can use ontologies for doing that. Because your model is producing some data, just have to add some semantics to the data, and then you can match these semantics to the semantics associated to your user. Because your user is interested only in a sub-list of topics, only the data which are near me regarding my house, my neighborhood. So the whole process that Thierry is building is all to make this matching between here is my data and here is semantic description of what my data is, and here is my user and the list of what he is subscribing or what he is interested in. And the whole process of Thierry is how you make this connection between those two automatically because you have made the work of describing the ontologies.
Yes. You need to describe the vocabulary and also the relation between all the concepts, all the entity you have. And after you can make deduction and say, well, because you are interested in this, because you are here, because, okay, I make the connection.
But warning systems in more global way, I think it's really a good application for that because you really want to focus your message only on a sub-list of people which will be really reacting to your message. Don't want to just flood the whole city with a warning system and provoking a panic. So
yes, yeah, you have to target
definitely
messages
something
there.
you should have a look at it.
Some people work on ontology on disaster management. There are some papers.
One question for you, Thierry. You are working with a lot of students' team and they are producing a lot of projects. What was the funniest project for you that you've made around IoT? Because I've seen that you've shown us a smart hamster.
This is the most funny one. Fitness hamster fitness center. I don't know. It's a funny one. Yeah, hamster one. What I saw, it's students have many ideas. On IoT, it's very interesting to make the idea real. So it's a good way to make innovation with students, and they're happy to do that. So we create some teacher literature on IoT and innovation, and students create many projects. Perhaps not funny project, but it's an interesting project. For example, they make a project for bees on winter. It could be very cold in France on winter, and they need to feed sometimes the bees, but they need to do that at a good time when it's necessary, because each time they feed them, they kill them some of part of the bees. So they create some IoT system to know the temperature inside the bush on a place. Hives. And also to know where are the hives, because some people store the hives. And they create a specific application for this and create a company behind it. So there are many projects like this where a student can create and do things very easily. And it's very funny as a teacher to see that and help them to manage this. Questions?
There's actually someone here today from a company that's basically doing edge analytics for, you know, companies all around Australia and the US.
It's Tom Mean.
So there's an expert in the room.
Usually I'll be hot, so good to say what else. I'm going to do that.
Thanks for both of your presentation. It's very interesting. I have two questions for you, Professor. Yes. There's two details. So when you mentioned, I remember in the second last slide, you mentioned the comparison between the responding time. Yes.
Mm-hmm.
So I was wondering, what's the impact of your model, of your structure, to the other indicators, performance indicators, such as what's the impact you bring to the prediction performance? What's the impact for the battery of the sensors after you change the structure? First question. Second question, in one of your slides, I can't remember the number, but you shows the rules. There are two rules. Let's say if the passenger is lower, and then like association rules. So I was wondering, the rules is predetermined beforehand, before you set up, or I mean, how you get the rules from? What did you learn the rules from? What happens if we change the rules? I mean, based on different scenarios, will that impact on the performance?
So first response for the second question. Yes, you need to have an expert that creates the rules and explain how we can infer knowledge inside your ontology. We don't work, perhaps there's some work to make some prediction and automatically create the rules, but from us, our works, we make the rules, and the goal is more to distribute the rules around the system. Focus on this. For the first question, this is also some work we have started in the PhD to see the impact of fog computing in terms of energy and also quality of services, what we can get in terms of response time. So that's why we work on iFoxing also to have a simulation of this. But it's true, if you make some processing at the level of the fog, you create more consumption in terms of energy. So you also manage this. You've got enough energy to do that. So you should also include in the model and to have some scheduling model to place also the services at a good place to have enough energy to manage this. So it's a PhD that work. I have another student that work on this since 1 year now. We have first result, but we need to continue to do that. So yes, there is a trade-off between energy, response time. If you are on the cloud, yes, you get no problem with the energy, but the response time and also some robustness. I saw some deployment of solution where company want absolutely to have the processing at the level of the phone, because they want to be sure that the service will be available even if there is no connection with the network and with the internet network.
Yeah, because we are just out of my curiosity, one of our project before was to do the fog computing on the sensor part, but it's for fires, it's for the security system. But eventually we find out that by theory it's working very well, but in practical it takes a couple of minutes to check it's for the security thing. It's not satisfying. I mean, it's not user friendly at all. It's too long.
It depends on application, and you need to have a modelization of the system before to distribution, and also it's depending on the evolution of communication system. Yes, there's a lot of parameters. That's why it's a research activity. And should wait a little before to have a ready application on real system.
Last question?
Thierry, from your experience in Europe about IoT deployments, that's why we started communicating on OM2M as an open source instance of 1M2M that the industry around the world is working towards. Here in Australia, we're still working in a landscape where vertical integration and proprietary solutions is the most preferred model by our good friends in the private sector. On the other side, from the users, clients side, especially thinking about councils for smart cities, they're going to end up in a situation where they're going to have a Sigfox, a LoRaWAN, a Wi-Fi based solution from a vendor. It's going to be all encapsulated. They're going to have 4 systems working in parallel, and they're going to be in a lock-in situation. So from the current situation in Australia, what is your take on what's happening in Europe? Is the industry moving genuinely towards an horizontal integration, or is the movement stalling a little bit in Europe as well?
I think some companies are well implemented. There are some solutions deployed on their world since many years, because machine to machine is not a new topic. It exists for a long time ago. But the problems they are faced on a problem of interoperability, because technology goes faster, and also I think city have new needs. And they saw that this vertical view is quite complicated to manage and will cost. And also it's take a long time to make an evolution and create a new services, a new usage inside the city, because it's vertical, it's totally closed. And if you want to get some information from one system and put in another one, it's quite complicated to do that. So I think the usage, what council want to do, what citizens want to have access, push the city to think about this and say, well, the system now can't work correctly, and it costs a lot to do that. So we need to have another way of thinking about our system of management of building, on light, on park, on all of those things. So we saw that some city, when they change the system, for example in France, I think in Europe it's the same, there is a new constraint in terms of light, street light. They need to save energy, so they change the system. And it's a good time to say, well, this new system, I want to have interoperability, I want to have standardization, I want these kind of things. So we saw that in different cities, when they change a system of street lighting, they think about this, and there is some companies that already propose some 1M2M standardization stack.
So it's
like
happening.
HP or this. Cisco work on this, but there are no customer from Europe, I think. So we see some big company that propose this kind of solution. So it's no, but it takes time, because they need to follow the cycle of high changes in the cities, there is a market for doing that. And also we need to have a city council that is open to this kind of idea. This is, for example, for Bordeaux, because people are involved in standardization, in smart city, this kind of thing. They are open to this kind of idea, and when they do a call to change the system, they ask to have 1M2M standardization. So it's come. We have we have some experiment in terms of proof of concept. On real implementation inside the city, it starts to come. It's a bet. I think this is a way of the future.
Okay, so thank you too for your presentation. Please join me to thank you.
Easy.